Okay, we're going to look at an application of vectors here where we have a salmon swimming in water that has a current, and we need to find the true velocity of the salmon, meaning we need to figure the vector of the salmon taking into account how the salmon swims in the water and then the effect that the water current has on the salmon as well. So we'll begin by drawing the salmon vector. The salmon swims north 36 degrees east at 5 miles per hour. So the vector looks something like this. And now we take a look at the current vector. The current vector looks something like this. So to get the true velocity of the salmon, we need to add these two vectors together. And so to do that would be easiest to find each of their components. So we would draw right triangles for each and then find the horizontal and vertical components very easily. So over here, this side up here, the horizontal component would be the hypotenuse 5, and it's opposite the 36 degree angle, so it would be times the sine of 36 degrees. And this side would be 5 times the cosine of 36 degrees. And you do the same thing with the current vector with the 70 degrees. Then you write each of the vectors in component form. So notice the vertical component here is positive, and the horizontal component here is also positive. Over here, the horizontal component is positive, but the vertical component is down, so it's actually a negative value. To get the true velocity vector, we add these together. And when we add the components, we get the vector 10.44, 1.31. So that is the true velocity vector. Just to visualize what the true velocity vector is, I've drawn the salmon vector and current vector tip to tail, as you do when you add vectors, and the blue vector here is the current vector. Okay? If I draw on the components of the true velocity vector, it's 10.44 and 1.31. They're both positive. You get a right triangle. The true speed of this vector is the magnitude. So you can figure the true speed by using the Pythagorean theorem to find the hypotenuse. It would be the square root of the 10.44 squared plus 1.31 squared, which is approximately 10.5. So the true speed is approximately 10.5 miles per hour. Now we just have to find the true direction of the salmon, which is given again by the true velocity vector. So what we'll do is we'll find this angle so that we can then get the bearing of the true direction. The bearing is going to be measured from north because this vector is going northeast, and you want to measure from either north or south. So we'll measure from north. We'll find this angle first, and then we'll find how far from north we are up here. Okay? So let's call this angle theta. The tangent of theta would be opposite over adjacent. If you take the inverse tangent of both sides, the inverse tangent of this number is approximately 7.26 degrees. So that's this angle inside the right triangle here. This angle would be 90 minus that, which would be 82.74 degrees. So the true direction of the salmon would be north 82.74 degrees east, because it's to the east of north by that much. So one more time, to get the true velocity, you add all the relative velocities. Notice the speed of the salmon is given relative to the water. That means the salmon feels like it's moving 5 miles per hour in the water, but the current definitely has an effect. You can see the true speed of the salmon is actually 10.5 miles per hour, not 5. And its direction is much different than its relative direction here in the water. So add the vectors, use components, use the trig functions to find the angles, and then measure as a bearing from north or south.